Okay, so this is lesson 8, problem number 6, the one that I said we would do. This is what you've done in lab, and this is what this is what you did in lab, and this is the problem that I promised I would put up on YouTube. So this is called finding the molar mass, and this can be done with any of the colligative property formulas because of the nature of each of the formulas has the term moles in it. So mole fraction has moles, and we use that in vapor pressure. And then the freezing point depression and boiling point elevation, there's molality, which has moles. And then in the osmotic pressure, we used molarity, which also has moles. So we can use any of the colligative properties to find the molar mass. And we do that first by finding out the concentration. And then using another thing, which is the mass. Okay? So typically, though, you'll see only freezing point depression and osmotic pressures are used because they show the largest dependence, which this is what we're doing in lab, or we did in lab this last week. And because it shows, and this should be largest dependence, okay? And so osmotic pressure is another option that could be used. So this problem is a great example, and it should help you with doing the lab. We're going to do step by step. So we have a 7.85 gram sample, and in lab this was our p-dichlorobenzene or our unknown, but this is our solute, what we dissolved. And it's dissolved in 301 grams of benzene. So this was our cyclohexane. And so this was our solvent, what we dissolved our p-dichlorobenzene or our unknown in. Now the freezing point of the solution, the mixture, okay, so this is solute plus solvent. The freezing point is TF, okay, and so this is not the of the pure benzene, this is of the mixture, okay, and so it tells you that it is 1.05 degrees Celsius below that of pure benzene. So what this really is the delta T. It's the change in, because it tells us that it was decreased by 1.05 degrees Celsius. And we want to know the molar mass. Okay, so anytime you're asked the molar mass of a compound, at least in this chapter, we're going to follow the following steps. First, we're going to write down our formula, which is that the delta T freezing, not final but freezing, is equal to the freezing point constant times the molality. So first we're going to take what we know, which is that we have the delta T and the Kf value, which were not given directly in this problem, but if we look back up here, the Kf of benzene is 5.12, so you would need a table or additional values given in the problem. We have the delta TF right there, and we're going to plug in the 5.12 degrees Celsius over molality, and this is molality is our unknown. So this is step 1. So we're going to solve for molality by dividing the temperature by the constant, and we're going to get so we're going to take 1.05 divided by, oops, I'm doing this with my calculator. This is going to give us 0.205 moles per kilogram. Okay, so that's the first step. The second step is taking the molality and determining the number of moles. So this is molality is equal to what? This is the number of moles is equal to what? So the formula is molality is equal to the number of moles of solute divided by the mass in kilograms. Let's write this out. Moles of solute divided by kilograms of solvent. Okay, so we have our mole value from up here. Those are the units. And we want to know this, which is our x. And we're going to divide that by the kilograms of solvent, which we're given up here, except it's given to us in grams. So we're going to convert that to kilograms. And when we multiply the 0.205 by the 0.301, that's going to give us the number of moles of 0.0617 moles. Okay, so that's the second step. So now, in the third step, we want to determine the molar mass of our unknown, which molar mass is mass in grams divided by moles of our unknown. So we have our mass, it's given to us up here. And we have our number of moles because we've calculated that now. And so now we're going to have 7.85 grams divided by 0.0617 moles, which in the end is going to give us a molar mass of 127 grams per mole, which is the final answer for the problem.